Okay, so good morning. I hope you had a nice weekend. I'm not going to say today anything about the weather because I have nothing positive to say about it. Okay, not what I see there at least. Okay, so so let's right away proceed toward our discussion of MBPT. We are interested in solving the eigenvalue problem, k psi nod equal k0 psi nod, where in our case k is the Hamiltonian in the normal ordered form, so it is h minus the expectation value of it in the state phi0, which is an independent particle model state. That is a single state determinant that we're using as a reference or as a Fermi vacuum, and also as an unperturbed state for the description of psi nod. Okay? Delta, the K0 here, the eigenvalue is delta E0, so it's a total energy minus the expectation value of the Hamiltonian in phi0, which is very easy for us to evaluate because we know how to calculate the expectation of the expectation value of the Hamiltonian in a single state determinant. Okay, and last time we essentially dedicated the entire lecture to define all the basic objects that are needed to formulate the Rayleigh-Schrödinger version of perturbation theory for this problem. So we split the K operator, or Hn in our case, into the unperturbed part, K node, and the perturbation, and we defined the unperturbed operator K node as, well, initially I wrote it as H0 minus the expectation value of H0. Okay, where H0 was defined as Z plus U, where Z is the one-body part of the Hamiltonian. Maybe I'll write it somewhere here. Okay. We are assuming that our original Hamiltonian consists of two pieces, the one-body part and the two-body part. And so we define H0 as the one-body part of the real Hamiltonian plus an approximation to V, which is a one-body operator. We call it U here. Okay. And then when we return back to K0, since we are shifting it by the expectation value of H0 in the Fermi vacuum, state phi0, that defines our unperturbed state, then K0 is simply the normal product form of Z and U. Okay, that is our K0. All right. Then we showed that this is a convenient choice because if we solve the eigenvalue problem for the little z and little u operators that define the capital Z and capital U in second quantization. So if we solve this problem, okay, for the corresponding spin orbitals or single particle states and the corresponding energies, single particle energies, then it's very easy for us to solve the eigenvalue problem for K naught completely. And that is, of course, a very important assumption in the perturbation theory. So we know that the eigenvalues of the eigenstates of K0 are phi0 itself, the corresponding eigenvalue, which I called kappa 0 last time, is simply 0, and that's because we performed this shift, which allowed us simply to calculate, to set the 0 level, right, to be simply the ground state or the energy associated, unperturbed energy associated with phi0, and then we demonstrated that for the, maybe I'll write it still here, for determinants which are obtained by exciting fermions from the occupied to unoccupied single particle states in phi0, we have a formula that I'm writing now. So they are eigenstates of K0, and the eigenvalues, we call them kappa, labeled with i's and a's of the determinant. And we proved that these kappas are very easy to determine. They are simply sums of the single particle energies corresponding to particle states A and whole states I. You just have to form the proper subtraction. So you take epsilon, say A gamma, minus epsilon I gamma, and I run it over gamma from 1 to n. So if I, for example, want to know what is the unperturbed energy associated with determinant phi IA, say single excitations, then the corresponding eigenvalue will be epsilon A minus epsilon I. For doubles, it will be epsilon A minus epsilon I plus epsilon B minus epsilon J. Is it okay? Yeah, right. So this is how the unperturbed problem looks like. Okay, it's exactly solvable, and that is important because, of course, that's a key assumption for using RSPT. Okay, then we worked on the perturbation. We demonstrated that the perturbation operator splits into the 1 and 2 body parts. Okay, there would actually be 3 body and higher many body parts if our original Hamiltonian had them. Okay, so it's very easy actually to generalize the perturbation theory MVPT that we're considering here for the case of having, say, 3 body forces. All you would have to do is to simply add more to the W. Okay, I'm not going to do this because it's really easy, and there is really, I would probably gain a lot of information in this way for things that I want to discuss in this course. So anyway, for the case we have where Hamiltonian has only 2 body interactions, then the perturbation splits, and we demonstrated that these 2 parts are, for W1, we have the new operator in the normal product form, which we call Qn, which represents the difference of Gn and Un. Okay, now Un is the same Un that you use here to define K0, so it's a known operator to us, and Gn is the operator that originates from the normal ordering of the V operator. Okay, so in other words, if you want to sort of write it more explicitly, this would be a sum. By that I mean, using cyclic quantization, this would be matrix elements of the little q operator. Okay, it's a normal ordering. We are talking about the normal ordered Qn, so it's going to be xr dagger xs. Okay, and the little q simply is defined here as little g minus little u. Okay, and we know both. Of course, typically we know them through matrix elements. That is, in cyclic quantization, that of course is the most natural way to handle this. So if I want to know what are the matrix elements of the Q operator that I need to stick here to define the one body part of the perturbation, I have to simply subtract the matrix element of the G. Sorry, I have to subtract the matrix element of the U from the matrix element of the G. And we know how to calculate both. For the G, I was watching this video, I noticed that I forgot to write a summation. You probably spotted this yourself. Okay, for the G, as you know, the definition of the matrix elements is R, I, V, S, I, anti-symmetrized, and you have to sum it over I. That's the summation I think I didn't write when I was writing it quickly last time, but I'm sure you know this anyway. Okay, so we know how to calculate this from the definition of the original V. Okay, we know the V, of course, so we know these matrix elements. And because we know them, we can easily determine the G. Of course, you know the U, because U is our choice. U, we are making the choice of U. Okay, so you would certainly not choose U to be something you can't calculate matrix elements for. That would be ridiculous, right? So we obviously, that's what we're going to do. All right? Okay. All right, so this is the perturbation. And having defined K node, having defined W, having defined eigenstates of K naught being simply slated determinants, okay, we proceeded to work out the many-body form or MBPT form of the reduced resolvent. Okay, this was the end of the last lecture where I demonstrated that if you take, in general, I'll simply take the kth power of the resolvent, okay, because we can have the resolvent itself or its various powers in renormalization terms of perturbation theory. Then we showed that you can split it into the various many-body components. So you simply have to form kth powers of each of the many-body component, and we have to run those many-body components from singles, one part to one whole excitations, all the way to n, where capital N means the number of Fermis you're trying to correlate. Okay, so the length of the resolvent in this form is the length of full CI problem. Okay, essentially. other than phi 0, okay? And we showed that because of our choices of unperturbed states, okay, the formula for the reduced resolvent, after working on it a little bit, okay, you remember we were summing initially over ordered sequences of i's and a's, then we got rid of the ordered, and then we showed that it's 1 over n factorial squared for the n-body part, and then we have a sum over occupied indices I1 through IN and unoccupied indices A1 through AN, and then here we have the excitation operator I1 through IN, A1 through AN, acting on phi 0, which really is a sort of a nice way of writing the, so I'm going to write it here, the n-tuplet excited determinant phi I1 through IN, A1 through AN, okay? Then we have phi 0 and the de-excitation operator, that is we have to take an adjoint form of E I with i's and a's, okay? Which is, of course, the bra determinant I1 through IN, A1 through AN, okay? So the cat and the bra come from the projection operator that you have in the numerator of the resolvent, and in the denominator we have minus chi I1 through IN, A1 through AN, okay, to the k, if your power here is k. If power here is 1, if you just look at the resolvent, then of course you just have the denominator. And you can see the denominator, there is a very simple rule that we'll of course take advantage of today. That is, you know, the original eigenvalues kappa are epsilons for the particles, minus epsilons for the holes. But we have a minus. You remember what the minus comes from? It comes from the fact that we have kappa 0 minus kappa of excited determinants, right? So kappa 0 is 0 in our case. That's why we have to take a negative of kappa, which means that in reality, perturbative denominators are easy to read. You take epsilons of the holes minus epsilons of the particles. And that's, you know, a rule that goes all across the entire MVPT, okay? So that's going to be easy. Okay, so now let me start commenting then on sort of what are the consequences for our expressions, you know, having these very specific forms, okay, of K naught, W, and the resolvent, okay? Well, the first observation that we should make is that all of our operators that we're using are in the normal product form, okay? You can see here we have a normal order of K naught, and we have a normal ordered form of W because we have Qn in it, and I guess I didn't write the two-body part. That's funny, but I guess I assume it's so obvious. So let me stick it here, okay? So W2, of course, is Vn, and we know what Vn is, so I'm not going to write it, right? We know that Vn is just the normal ordered form of the W, okay? All right? So in other words, you can see that our perturbation operator has the one-body part, which is in the normal product form, and the two-body part, which is also a normal ordered form. In other words, when you start computing expectation values of these operators in phi 0, you end up with a 0. Because we already proved long time ago that the expectation value of an operator in the normal product form, expectation value in the Fermi vacuum is 0. So one of the consequences of this is this. If I take an expectation value of W, it's going to be a 0. Okay? Well, that's interesting, because that now has various consequences on our sort of whole theory. Okay? To make sure I didn't miss any equations I wanted to have here to review this material. Okay, I guess I've got it. Right? If you see something I'm missing or that I need to remind us of, let me know. Okay? Don't be shy on these things. Okay. So anyway, so what are the consequences of these of the observation that the expectation value of the W is 0? Well, there are two of them. First of all, when you start writing the perturbative expansions, we know that the first order correction to the energy, okay, is an expectation value of phi 0. Okay? But you know, this means that there won't be any correction in the first order. Okay, I'll come back to this. You know, that means that the first correction worth considering is second order. Okay, in other words, there's no MVPT1 really for the energy. that you need to worry about. But there is another consequence which is extremely good for us in terms of practical aspects of our calculations. That is, you remember when we were writing these renormalization terms using, say, bracketing technique, okay, that we've learned. There are lots of terms there with expectation values of the w's. All of these terms will be gone here. We don't even have to write them. Okay, they exist. So of course, when you work out your bracketing technique for, say, 10th order, then you would have to, of course, make sure that you're checking all the terms, but you will not have to worry about bracketing a single w, because all those brackets will be 0. Okay? So when I start writing the expressions, well, we're learning something very useful, that the first order correction to the correlation energy is simply 0. Okay? The second order correction, okay, there are no renormalization terms there, so all you need to write is W R0 W. I am assuming that you remember that this symbol here, this bracket, means bracket in phi 0, our unperturbed state. Okay? Do I need to explain, or can we assume that we are all now aware of this? Okay? What about the third order? Well, third order is the first term where we had renormalization terms. Okay? So if I wanted to, of course, be truthful to RSPT, okay, I would have to subtract here the expectation value of W in phi 0 and then have W R0 squared W. But you see, I don't have to do this in MVPT. I would have to do it maybe in some other perturbation theory, or I would have to do this if I didn't use normal ordering. So hopefully you can see now why I insist on this normal ordering. Yet there's yet another simplification. I don't need to carry so many terms, okay, because that will be gone in our case. So we'll just end up with the principal term. Well, that's interesting. That's nice, right? Because that simplifies. Certainly you can see the computational advantage of that approach. But there is more. That means that the first order that where we see renormalization terms is fourth order. Okay? So there will be, of course, a principal term there, which is W, R0, W. Why don't I write it in this compact form? Okay, R0, W cubed, R0. This is R0, W cubed, and then W in front. And then, you know, you remember there were some renormalization terms that contain the expectation value of W and the square of that. I'm dropping this out now. Okay, so I'll just write the only term that survives. Maybe I'll emphasize here, under the condition that W, expectation value of it is 0, right? Under this condition, all we need is one term, one renormalization term, W R0 W times W R0 squared W, okay? All right? That's interesting, that's useful, that's very simple, that it will allow us to calculate this quickly. However, that's also important because of the fact that when, you know, when Brachner noticed the linked cluster theorem, sort of that may exist. The fourth order correction to the correlation energy was the first order. You know, that's where the discovery was made. You can understand now why. Because there is, you know, the linked cluster theorem is about cancelling. Some terms, cancelling renormalization terms with the so-called unlinked diagrams in the principal term. Now, we're not going to have any renormalization terms to third order, so there is not anything to cancel. Okay? So that's how historically the discoveries were made. By looking at that order, okay? And of course we can write more. I'm not going to do that, you know how to do it. Everybody did great on the bracketing in the homework, so I'm certainly happy, okay, about that. Let's maybe also complete this list of wave function corrections. Maybe I can still try to see it here, sorry. Okay, for wave function, the same thing. You know, if I start writing the first order, of course, you know, it is just R0W. So no renormalization terms here. Maybe I'll write it after semicolons. You know, for the second order, okay, we have R0 W square phi 0. That's the principal term. Okay, and then of course normally you would have to write the expectation value of W and square of the resolvent W phi 0. But again, because of the fact that bracketing single W does not produce any non-zero result, we end up with a 0 here. So we are just left with R0 W square acting of phi 0. Okay, so if you want to see renormalization terms in the wave function corrections, you have to go all the way to third order. Okay, and this will give you R0 W cube phi 0. Then of course there are lots of renormalization terms that contain the expectation value of W. I'm not going to write them, so again I'll write this expression under the assumption that expectation value of W is 0, then all I have to write is just one term with a negative sign, W, R0, W, times R0 squared, W phi 0, okay? As you know, this is a perfect analog of K04, okay? So I can just drop here this part, and I'm going to get 4 order. So I'm going to get second order correction, third order correction to the wave function. Okay, so those are consequences that we have from the fact, that originate from the fact that we are using normal ordering. No correction in the first order, great simplifications in higher orders. The first time you see the renormalization terms, please remember this, because that's how we're going to go in this course about that, is third order correction to the wave function. That's where we have to start looking with some magnifying glass and see what happens there, okay? And fourth order correction to the correlation engine. That's again where we'll have to start seeing, is there something interesting about it, the cancellation diagram. Okay, that's how we're going to be setting up our stage. Okay, so to summarize, our correlation energy, that of course, I said, strictly speaking, correlation energy is relative to Hartree-Fock reference, but let's treat it loosely, anything beyond mean field. Okay, so that's delta E0 is simply a sum of corrections. Okay, let me recall what delta E0 is one more time. So we have this here. It starts with the second order. Okay, and then it goes on. Okay, so the lowest order in energy that you have to worry about is MVPT2. Okay, that's how we actually say those things. All right, so this is, when you see papers, when people say MVPT2, what they mean by that is the MBPT truncated at the second order. When they say MBPT3, you truncate third order. Of course, precisely you should say order of what? Energy of wave function. So if you want to say, oh, I truncated my wave function at order 2, then that means going all the way to psi 0, 2, okay? Well, that means that I should say MBPT2 in the wave function. If you don't say in the wave function, you may confuse your reader. They will not know which MVPT truncation you're talking about, okay? And this is important because actually, the fact that correlation energy starts with the second order was discovered initially by Miller and Plesser. I mentioned those names last time, okay? Already in the 30s. So it's an old story. And you may sort of try to wonder, I don't know if you're wondering, why is it second order? Why is it first order doesn't do it? Well, okay, I give you a reason, normal ordering, right? But you can say, well, yeah, but you did normal ordering. Is there a simpler explanation than that? Well, there is, of course. Look, imagine for a second, okay, that I started what I would consider to be on the wrong foot, okay, by trying to use perturbation theory directly to the original Schrödinger equation, okay, without doing this shift. Okay, so if I did that, well, and assuming that H is Z plus V, well then, of course, I would end up with corrections. Okay, I would have E0 written as E00, okay, then E01, and then E02, and so on, right? That's what I would come up with, okay? And E00 would be sum of single particle energies, as we proved last time, in phi 0, okay? Our H0 would be Z plus U. Our perturbation, I'm going to call it tilde maybe because not to confuse with the W we're using, which is in normal ordered form, would be V minus U, okay? Essentially just so that the two of them add up to H, okay? And now if you really pay attention closely to what are the formulas for corrections. What is E00? Well, that's an expectation value of H0, okay? Obviously, because P0 is an eigenstate of H0 by definition. What is the formula for the correction to the first order correction to the energy? Well, it is phi 0 perturbation phi 0, right? But H0 plus perturbation, of course, gives us H. So if I add the first two corrections, I mean the zero order correction and the first order correction, I just end up with the expectation value of the Hamiltonian. Okay, can you see this? That's the real reason, okay, that if you don't want to insist on normal ordering, you pay sort of a price in simply dealing with first order, which really doesn't bring much information, because the sum of these two is simply the expectation value of the Hamiltonian, which is sort of, say, Hartree-Fock energy, phi 0 is Hartree-Fock, okay? So you would be simply overcomputing. You would be keeping first order corrections artificially. Those first order corrections don't really bring new physics, because that physics is already in the mean field value of the Hamiltonian. Okay? Is this clear? That's very important. And that's actually, when you look at the paper of Miller and Plesset, they didn't use second quantization. They used first quantization, you know, the Slater rules in a conventional form, the Coulomb exchange operator, so the paper is very long to finally produce the correct formula for the second order correction. But the paper has this message to all of us, that the real reference energy for us should not be E0, which is a naive sum of single particle energies. That's not a good reference energy. Your reference energy should be expectation value of the Hamiltonian in phi0, because that's sort of, for example, Hartree-Fock energy. That's what Miller-Plesset did. Okay, they were correcting Hartree-Fock energy. And they noticed that simply it is not useful for us to consider the naive sort of look at perturbation theory where you're just summing the unperturbed energies, you know, the E, the epsilons. Okay? Because if you sum the epsilons, you don't bring any information about interaction. And it's very easy for us to accommodate some form of interaction that is through mean field. Okay? So that is, to me, actually one of those key moments in history, right? Because Miller-Plesset were the first to really analyze this and said, look, if this is our, you know, if you proceed this way, that's going to be really, up to the first order you're done, you're still not bringing correlation because it's all still in the expectation value of the Hamiltonian in phi0, okay, in the Slater determinant, which means that the first time you see something meaningful for the correlation is the second order, okay? All right, that's history. Okay, now we're going to go to more recent times. We now have to work out. We now, of course, you know, go to the diagrams. Okay, as you know, much of this course is about diagrams. So what we want to do now is we want to calculate these various perturbation theory orders diagrammatically. Okay, first, you know, just to learn how to do it. And the next thing is to uncover some fundamental theorems behind MVPT, which you can only see, well, historically at least, you know, if you want to discover them, you really should use diagrams. Okay? All right. So in order to do this, we have to realize what kinds of expressions are we about to calculate here. If you look at any perturbation theory orders, and I am keeping them there just so that we can keep looking at them, you know, there are two kinds of expressions. There are energy expressions, or energy corrections, right? Which always have the form, which if you look at any term in energy, you're going to have phi0, perturbation, resolvent, okay, you know, either in the first power, in the principal term, or in some other power, if it's not the principal term, maybe, then W, then another copy of R0, and of course you continue like this, the last terms being, say, R0 in some power, I'm going to call it N gamma. Let's assume that we have gamma resolvent in this term, okay, then W phi0. Where all these N powers, or these exponents, N, so let's call it N alpha, are greater or equal 1, and to be formally correct, alpha runs here from 1 to gamma. So I'm assuming that I have gamma resolvent in my expression. This is how a typical or a general expression looks like when you start looking at energies. And next, the key here is, so maybe I'll make a remark, that's how, what K0 has in it. Okay? K0 corrections, I should say, have them in them, right? If all those little n's are 1, this is the principal term. If some of them are some higher powers, of course, you may end up with some renormalization terms, and of course then you have expectation values of w's and so on and so forth, right? So I'll sort of leave it at that. Okay, all right? Well then we have also wave function corrections. Okay? So let's talk about them now. Well, there, as you can see, still some examples. We always have the first term, okay, is the resolvent, which is either in the first power or in some higher power. So I'm going to again put, say, power n1 to be more general, right? Then I have a W, then I may have another resolvent if I'm in sufficiently high order, okay? And then you continue, and your sort of last term, so the last terms in the expansion will be, say, again, R0 to, let's call it N gamma, okay? And then W acting on phi0, okay? So again, these n's can be 1, that's the principal term, or greater than 1, some of them at least, right? When you're talking about renormalization terms, some squares, cubes, and so on. Of the resolvent, we've seen this multiple times already, okay? That's what we are facing. We need to learn how to use diagrams, our rules that we developed in this semester, to compute these corrections and corrections to the wave function, okay? We know that our W is the sum of 1 and 2 body parts, okay? And we know that the resolvent is the many-body operator that contains various n-body components running from 1 to n, okay? Those are the key objects. We need to know then how to represent diagrammatically W1, W2, and the n-body part of the resolvent to be strict in arbitrary powers, because we may have powers of the resolvent in the renormalization terms. So we at least, at this point, maybe I'll also put here K. You can do the same, not essential. We don't know it, okay? But anyway, those are the objects we need to know how to represent diagrammatically. As you will learn, okay, so, those of you who already heard a little bit about perturbation know that nobody draws resolvent diagrams, okay? Well, eventually we'll learn how to get rid of them. But in order to learn how to get rid of them, I want to first draw them, and then learn that, I'm wasting my time. I can develop some extra modifications to the diagrammatic rules that allow me to simply skip the resolvents, okay? But I will have to modify the rules then, accordingly, which is benefiting you both, because nobody wants to draw diagrams that are really not that essential, right? If we can just modify the rules. So this is going to be an example of the fact that we have these general rules that we developed so far, but when you come to specific many-body theory, sometimes you do the modification in the rules that allows you to handle certain kinds of expressions. The same applies to kappa-capacitor theory, okay? Of course, you always start with the generic rules that we developed, but then in kappa-capacitor theory, because it only has a certain kind of expressions, you may say, oh, you know what, I'm going to modify them to so I can do this quicker, right? So that's how we proceed. And in every other maybe not in every, but in many cases, other cases that in kappa-capacitor, you may proceed in the same way. Okay, so let's talk about. Well, all right, W1, W2 should be obvious to us, but to be sort of complete in this presentation, I will start with them. So what is W1? W1 is Qn, right? It is a one-body operator, which I already defined, so this is really a repeat. Okay? So it's a one-body operator. We know what the G is. We know that, what the Q is. We know that Q is G minus U, so we know how to calculate these matrix elements. We talked about it already. Okay? It's a difference of R, G, S minus R, U, S. I think I also gave you last time another form of it. If you add Z to here, to this and this, okay, you remember when I add Z here, that's a Fock operator. And when I add Z here, so if I add an extra Z here and an extra Z here, of course they cancel out, but if I do this, then the first term is simply matrix element of the Fock matrix. That's a computationally convenient thing, okay, because we often have routines to compute Fock matrix elements. And then you subtract here epsilon R delta RS. You remember that? Because Z plus U acting on R gives you epsilon R acting on R, times R, right? You remember that? I think when I was analyzing W1, I said a little bit about that, okay? So the one computationally convenient way to compute these matrix elements of the Q is to take matrix elements of the Fock matrix and then subtract on the diagonal, okay? Because of the delta RS, if you write it as a little matrix, you subtract on the diagonal the epsilon R's, okay? So essentially the Q measures the deviation, okay, from the G. Okay, as we discussed. Okay, what is the diagrammatic representation? Of course, diagrams are easy for us to draw. It's a one-body vertex. If I use the Goldstone representation, maybe I'll write here Goldstone. It's going to be something like this with R and S. We just have to decide how to label our vertex. I'll be hanging a triangle here to be actually consistent with those by Professor Paulus. Okay, so not to deviate from them in this way. Okay, I'll hang a little triangle at the vertex. Okay, in the Hugenholtz case. Also one body vertex, but then of course we don't have to write these dashed lines here. Okay, we can just stick the triangle edit. Okay, again, label behind R and S. Well, in this case, the situation is straightforward. The weight in each case is 1. So the weight of Qn in the goldstone case is 1. We have one open path only. Okay, here the weight in the Hugenholtz case is also 1. Okay, we have two lines, but none of them, they are not equivalent. Okay, for the scalar factors, maybe I'll write it for both at the same time. So when I put this x here, x will be either G for the goldstone or H for the Hugenholtz. Okay, so the matrix element simply labeled by RS is RQS, and the operator part of in each case, when we wrote, you remember the capital O. We're coming back to diagrams. That's a normal ordered product, normal product of XR dagger XS. Okay, which you can read from a diagram. So altogether, these expressions, the diagrams that we have here, of course, are natural. They are of course natural to us. They fit the sort of the formula that W1 is the weight of Qn in either representation, so that X here means goldstone or Hugenholtz, whichever you choose. Okay, then you sum over indices of a diagram. Then you have scalars, which are either of the goldstone or Hugenholtz type, but in this case both representations are really equivalent when it comes to matrix elements. And then the operator part, which again is the same for goldstone and Hugenholtz. Okay, I'm writing this because we can use both representations, so I want to be sort of complete on this, but you know very well that there isn't any difference between goldstone and Hugenholtz for one body. Okay, well then of course we have two body. Alright, again, two body is actually very well known to us because the W2 is simply the normal product form of the V operator of the same V that you have in the original Hamiltonian. Okay, so we know that we can write it either in terms of the say RSTU here, non-symmetric matrix elements. Okay, and then we have a normal product of let's see, I want to put it this way. Okay, so XR dagger XT X S dagger XU. Okay, or in the form that is good for the Hugenholtz representation, where we use the anti-symmetrized matrix elements RSTU, so the A symbol here, and then the same normal product. Let's see if I can squeeze it. XR dagger XT XS dagger XU. Okay, and diagrammatically, of course, that's a quick refresher. Okay, for the if you use the goldstone representation. Okay, this will be an appropriate vertex, say R, S, T, U. Okay, for the Hugenholtz case, you will just have 4 lines at the vertex, so we have R, S, T, U, and the Hugenholtz. Okay, and then when it comes to identifying various key elements, so the weight of Vn in the goldstone case is 1/2. There are 2 equivalent open paths. The weight in the Hugenholtz case is 1/4 because there are 2 pairs of equivalent fermion lines in the diagram. The scalar in the goldstone case, labeled by RSTU, is the non-symmetric matrix element RSVTU. In the Hugenholtz case, you have an anti-symmetrized form of the same matrix element, so it's RSTU, RSVTU with an A symbol, script A. And for the operator parts, they are identical in both cases, so I'll just write that again, maybe using this X being G or H. So I'm going to say that for each representation, our operator part is the normal product of X dagger X pairs, right? X dagger R X T for this pair, and then X dagger S X U for the other pair. Okay, so altogether W2 meets our requirement. Then we have the weight Okay? In Goldstone or Huga's representation, I'm going to use this symbol x, which can be g or h. Then we're summing here over indices, r, s, t, u. We have a scalar part, which is, of course, depends on the representation. Okay? Because we have non-symmetrical or anti-symmetrized matrix elements. And then there is an operator part, okay, which actually does not depend on the representation. It's the same in both, but I write it like this, okay? So those are familiar things to us, right? The only new element here is what kind of symbol will be sticking in the Q, because we never dealt with Q before, okay? So I'm going to use a triangle, okay? All right, so what is new then? Well, the new thing is the resolvent, okay? The new thing is the resolvent. So let's think of an appropriate formula. But as you remember, so first of all, what we need is in general, the kth power of the n-body contribution to the resolvent. Well, let's write this formula, because now we'll have to find the proper representation. That's a new object. We've never dealt with this before. Okay, so we have a summation of i's and a's. Okay, we have here the excitation operator E, I1 through IN, A1 through AN, okay, acting on phi 0. Then we have the bra phi 0 and the de-excitation operator, I1, IN, A1, AN. Okay, meaning that I have to take a Hermitian adjoint of it, and then I have to divide it by the perturbative denominator minus kappa, I1, IN, A1, AN in our K. Okay, and maybe as a reminder, how we define these operators. So E, I1, IN, A1 through AN is the product of creation and elimination operators. You know, these pairs corresponding to excitation. So we have XA1 dagger XI1, and then after some dots you have XAN dagger XIN. Okay? And for the de-excitation part, let me also write it, because now I'm going to be sketching a diagram, so I would like to have all these pieces in front of our eyes. Okay? If you want to take a dagger, you have to take a dagger of this, so you write, so you end up with XI1 dagger XA1 and then XIN dagger XAN. So in other words, we are now creating holes, okay, and annihilating particles, because we are doing the de-excitation, okay? So now, you see, you remember we talked about this sort of idea of this class that we're designing diagrams, okay? We're sitting here like architects and we're thinking what would be the proper representation, okay? Rather than me just telling you what the representation would be, all right? Without explaining. Okay, so what do we see? Well, maybe I'll now start using color, okay? More of it here, all right, good. Well, from your experience, I'm sure you already expect that this will be the weight, right? Because we always have this situation where each of these numerical factors in front are always weights. So our representation has to reflect on that. Somehow, it has to be 1 over a factorial square. Well then, if you look at this carefully, you can see that, there's this operator part, this and that, okay? Those will be our operator parts. Okay? So when we design, we have to somehow reflect on this by simply setting up our Fermion lines so that they reflect on this particular composition of our expression, okay? And then, of course, you can expect, maybe I'll use a different color not to mess this up completely, right? Certainly this middle part somehow must be read, must be a scalar, right? Must be read from a diagram as a scalar, because that's the only number you see there, other than the factorial square, okay? So let's start building a diagram. And let's start with a Goldstone representation, which typically for building diagrams is easier to follow through, okay? So, okay, I have an excitation vertex. You remember, it's a bunch of simple vertices. Let's emphasize 2 of them here. You have A1, I1, okay? That's the first creation-annihilation pair. Then you have A2, I2, and then after some dots, you end up with the last one, which we're assuming here n-body, so it's going to be ANIN, okay? So I have n simple vertices for each of these x dagger x pairs. I don't want to treat them separately, I have to hook them up together, bundle them together. Remember the idea of a super vertex. So I'm going to simply draw some lines with, that allow me to connect these things together into the excitation vertex. And I'm going to sort of connect them to some sort of a thick ball. Okay? All right, how about that? Right? That's fine. For the design, it's fine. Okay? So this part, clearly, maybe I'll move it up a little bit. You can see that this part here must represent our excitation vertex, our excitation part, the E operator. Okay? You see it here. Okay, this E. Okay? That's this part. Well, I have a de-excitation part, so I must have like a mirror image for this particular part. So I'm going to start by, again, you have A1, I1, A2, I2, and after some dots I have AN, IN. Well, of course, this time everything is reversed. A's are coming in, I's are leaving, right? Because it's a de-excitation operator. Again, we have these simple vertices which we have to bundle together. So I'm going to use some sort of an open circle, I guess, to be a mirror image of the dark circle here. Well, not dark, really, it's actually white. Right? Anyways, it's got to be dark in your notes, yeah. Unless you're using a blackboard. Somehow. I guess nowadays you can do everything, right? You can probably buy a little iPad which will have a blackboard, right? And then you write with white on black. That would be nice. I think Khan, this is Khan Academy. That's what he did, right? He did some sort of electronic version of the blackboard, which I think is fantastic. Okay, anyway, so that's what you have. So right now what we have these two elements, the E here, and that's that's a de-excitation. Maybe I'll also mark it, that this part somehow reflects on the presence of our de-excitation. I1, IN, A1, AN. With a dagger, right? Okay, I'll move it up a little bit. But of course, that's not fine, because that's just the product of E and a dagger, okay? You need the rest of the diagram in this, okay? So you have to connect, anytime we want to bundle these things, we have to put extra symbols. So I'm going to do the following. I'm going to put here, okay, a big circle, and I'm going to stick K in it. That circle will remind me a few things. First of all, it tells me these things are not independent. You have the same indices AI here as here. They are not like running loose completely, right? They are really related because that's how the expression is. K tells me that I have kth power, okay, of my resolvent. Kth power. So I'm going to put that K. And I will simply interpret this middle part as the middle part of our expression. What's the middle part? Middle part is phi 0. Let's not be too generous with space. Okay. So this part here, okay, is maybe middle part here, okay, is phi 0, because that's what you see right in the middle, divided by minus kappa I1, IN, A1, AN to the K, okay? Now it looks like I've got a diagram, maybe a bit too complicated for general use, but a diagram that simply has everything in it that I need to have, okay? So, let me maybe put it up so you can see it better, because I can still use my pointer, okay? And maybe then we'll have a little break, okay? So, you can see this diagram has everything you need to have in a proper representation. What do we have is excitation vertex for this, de-excitation vertex for that, okay? We are bundling this together and the middle part is represented properly, okay? Because we'll remember simply how to represent this region, how to read this region. What about n factorial? Well, we are fine here too. You see, I have n equivalent open paths. I can permute them in n factorial ways. I have n equivalent open paths here. That's another n factorial. So altogether, the weight of this diagram is n factorial squared. 1 over n factorial squared. You see that? So it's a fine representation. We may argue whether we like it or not, but it's a fine representation. So maybe before the break, let me show you another thing that I can do with it now. I'll erase this because that's kind of obvious to us. I can simplify this representation. Because, ultimately we want to simplify it and eventually, of course, learn how to get rid of it altogether. Okay? Let's see if I can push this. Okay. You can see there's a certain logic in it. Let's imagine I start here. I go with A1, go through a diagram, cross it, and leave with A1. So I have sort of that long sort of trajectory here, right? That starts with A1, leaves with A1. The same here. You have an I going through and leave with an I. Okay? So because of this sort of pairing between the left and right parts of our diagram, it seems like we can simplify it to this sort of more, I would say, Huguenot style representation. We have a line A1 that enters the resolvent, goes inside it, and leaves as A1. Sorry, what am I saying? Okay. I don't want to blame Monday for this. That's my fault, not Monday's fault. Okay? It's A1, alright? So you enter with A1, particle, go through a sort of this middle region and leave as A1. Then I1, you enter, go through, leave. And then you do it for A2 and I2 and so on. So I'm going to put some dots. So if you really look at this, we have AN here, AN, and IN passing through as IN, okay? We'll certainly have this in that picture. Moreover, you know, there is this middle part, but I can easily learn how to accommodate the middle part by simply slicing these lines and hanging K. That K will just remind me that it's K power. You know, for now we'll be doing this, because if you don't do this, you may forget it was K power. You may forget it was a resolvent with a square, right? You know, these renormalization terms have all kinds of R0 power, so it's safer for us, for now, to register it, although this, you know, later we may learn how to not to do all of this. This is also a fine diagram. What is the weight of it? This time, we have N equivalent Fermion lines A, and N equivalent Fermion line I. Okay, so the weight is certainly 1 over N factorial squared. Okay, maybe I put the weight of R0 N, not needed one. Okay, alright? Just like that. For different reasons. Over there, it was N open paths on each side, giving N factorial square. Here we're talking about Fermion lines now, directly. Okay, what is the scalar factor of it? Okay, I'm going to write it like this. Use my notation from the notes. Okay, so this here I have K to just as a reminder, it's a K power. You know, if you really look at the expression, you know, that we have, the middle part should give you the scalar information, right? Okay, and you know, so what we have there is minus kappa I1, IN, A1 through AN to the K. Just as a sort of refresher, what is it actually? Well, this is a sum of epsilon I gamma minus epsilon A gamma, summed over gamma from 1 to N, and taking the K, or the negative K actually, negative. It's in the denominator, okay? So please always check me out. Yeah, if you see some error, always tell me that you see, look, you know what, you forgot to copy something. Right, there's minus here, all right? Okay. What is the rule behind it? Let's go back. I can learn about this denominator by simply slicing these lines. See, it's very easy to remember. You simply look at, you slice like with, knife. You slice your diagram, okay? And then you take single particle energies for the lines that go this way, minus single particle energies for the lines that go that way. Okay, that's what it is. So the rule is very simple. You read the scalar by slicing the diagram. And that K tells you what is the power you take, and of course you put it in the denominator. That's why I put here minus K. Alright? And then the operator part, if I use this form, okay, the operator part then, also labeled by indices I1, AN, and A1 to AN, is simply what's in the middle. Right? So in the middle what we have is, we have an excitation operator, okay, because we certainly see the excitation to the left of the dashed line, and I have the de-excitation operator here, and in the middle, let's agree simply that this line tells you phi 0, phi 0. The presence of this dashed line slicing through gives you two things: denominator and the phi 0, phi 0 that you have, from the projection operator in the resolvent. Okay. So the way to read it is phi excitation operator, then phi 0, phi 0, and the de-excitation part of it. Is this clear to everybody? Or you have any question? You know, I'm just sort of trying to give you a good rationale why this is a proper representation for what we want to do. Okay? I can read everything on this picture. It has everything you need to have. It has the right weight, the right scalar, because you just slice it through and you read from it. Okay? And it has the right operator structure. Excitation, de-excitation. Okay? Everything according to our rules. So that means that the resolvent, not right now, maybe that's before the break, the last thing I want to say. In this representation, it really satisfies our requirements. It's the weight, okay, times the summation over indices of a diagram, and then times the scalar, which is defined as these perturbative denominators. So I'm just writing the scalar. I1, IN, A1 dot 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 AN, and then the operator part, okay? I think I need a dash here, okay? I1, IN, A1, AN, okay? So you can see that with this representation, our reduced resolvent satisfies the rules of diagrammatics. You remember, the rules of diagrammatics, the theorem we proved, requires that every object is weight, scalar, operator, summed over indices appropriately, okay? If you don't have this structure, can't prove our theorem. I want to use our theorem, our, you know, remember, our Week's theorem in diagrammatic form. If I want to use it, I have to have this. And my representations, all of the things we are using, must be represented such that I always have the weight, the scalar, the operator. If I have that, then I can use our rules, okay? So maybe here, let's have a short break, maybe 5 minutes, okay? And then we'll start doing MVPT in the second order for energy, okay? With this knowledge and learning about possible additional simplifications. Okay? Alright. So let's have a... In the meantime, of course, I will do the homework. So... Okay, Mark. Is not here. Yeah, well, you know already, probably, I'm sure you looked at your blackboard, right? So, perfect work, guys. I really have. Yeah. You know, I tried so hard to subtract 0.5 points, I couldn't. No, I'm joking. I don't do that. Anyway, that's for call. Yes, cool. This is your fantastic work. Please read the comments though. Sometimes, you know, even though the work is fantastic, I still make little comments. So we always read them, you know, because they may be of some use, right? For the future reference. How are you doing? Yeah, so of course, if you have any questions, yeah, Wednesday will, please collect some questions. Of course, you can always ask me any time, right? But we'll try to handle the questions, right? I have to check this room. I wanted to check it on Friday, but they close these buildings after several hours, and I don't have keys to the crowd. Do you? Can you enter the crowd building yourself? I can't. My card. I was stuck. So let's slowly restart, okay? So now, okay, what we want to do now is, we have a representation of basic quantities, the W1, W2, and resolvent, okay? We know the diagrammatic rules for generic problems, our theorem that tells us how to handle the sort of the Weeks theorem in diagrammatic sense, right? So now let's apply these rules to low perturbation orders, okay, to learn about, first of all, to see the expressions for the first time, okay, and the second thing is, of course, maybe to learn if we can further simplify the rules or modify them. Okay, we have two kinds of expressions, so, let's first state the obvious. We have the energy expressions, and we have the wave function expressions, okay? For the energy expressions, we have expectation values in phi0, meaning that we have to draw all possible diagrams from the W and R0 vertices that have no external lines. That's as much as we know right now. Okay? Now for the wave function, as you remember, we have an operator part acting on phi0. So we have to draw diagrams that have external lines extending to the left. But you see, in MBPT, the nice thing about MBPT is that you really don't have to I should say you don't have to remember about it, but it's really sort of guaranteed by the presence of this leftmost resolvent. See, because you always have at least one resolvent in the leftmost position, if you look at this representation, you really have a situation like this. This first resolvent, the R0, what is it, N1 there, right? To the N1, okay? It contains, I'm just going to sketch it. Here N1, right? We have sort of a resolvent that has lines A1, I1, say AN, IN, if it's an n-body part of it. Okay, so this is this resolvent. Then we have a W, and then we may have the rest of it. Okay, so then we have some W, and then at the end we have phi0. Okay. But remember, in our interpretation of diagrams, that line that is used here really contains in it the information about this projection operator. Okay? So in other words, what we really see here is, we see here really phi 0, okay, in the middle, and on this side of phi 0 we have an excitation operator, okay? And on this side, of course, we have a de-excitation operator, then the W, and then the rest of the expression. In other words, here I have a, some operators, and eventually bracketed with phi 0. And some of the indices. So if you realize this, you can see that the rule that we have to extend lines to the left is sort of pretty much guaranteed by the presence of the resolvent. It is the resolvent that tells you that your lines that are, the external lines must be extending to the left, and they must represent particles and holes. Okay? So MVPT guarantees this by the very nature of the expressions. As you know, in other considerations, we may not have that, right? Because if we don't act on phi 0, we will not have this. But here, this is guaranteed by not only by our rule that you are acting on phi 0, but also by our structure of the resolvent. Okay? Alright, so let's then, with all of this knowledge, and maybe I should say, of course, the obvious, as you can see, in every expression we have, we are summing over indices. We don't have fixed indices here. We only have free lines, free indices, and that is, of course, as you know, somewhat of a simplification, because that means that, all the lines we'll be drawing will be free lines. Okay? Of the particle of whole type. Okay, so let's start with the second order correction to the energy, K02. The formula for it was phi 0, W, R0, W, phi 0, right? Remember, W is W1 plus W2. Okay, so I can split it further. Okay, I have W1 plus W2 here. I have W1 plus W2 here, so I end up with 4 contributions. Okay? Those 4 will be phi 0, Qn, so I'm going to start writing explicitly. Remember that W1 is Q, and W2 is V. Both in the normal product form. So we have, if you pick up Q from here and Q from here, you end up with this expression. Qn resolvent, Qn phi 0. Okay? Then, you will have phi 0, Qn from here, R0, Vn, and then phi 0. Okay? Then, if we pick up Vn from the left W, and the Q from the right W, then we have Vn, R0, Qn. I don't think I need that dash. Okay. Alright? Phi 0, and of course if you pick up V and pieces from both W's, you end up with the 4th contribution. Phi 0, Vn resolvent, Vn resolvent. Vn phi 0. So I'm going to call these 4 pieces K0A, so K0 second order piece A, that's this one, plus K02B, that's the second one, where you have QV combination, then K02C, that's going to be VQ combination, and K02 with a D, it's the 4th one with the 2 V's in it. Of course, you remember that if you have Hartree for phi 0, then Q is 0, then you only have the last piece. Okay? So, perturbation theory becomes much simpler if you are using a Hartree for reference. Okay? Because you don't have to write these pieces A, B, and C. But we will here, because we'll not, have a generic case. Okay. So let's process these cases. Maybe now I'll go up. I think what I said already here is being discussed, so I erase this. And let's now start processing. Let's start with the A piece. Okay? And let's just stick to the rules we know so far. Okay. So K02, second order correction to the energy, the A contribution of it, okay, which is phi 0, Qn, R0, Qn, phi 0. Well, what we need to do, we need to consider a product of 3 operators represented diagrammatically. So for the Q, okay, we have, say, RS and a triangle hanging at the vertex, okay? For the resolvent, well, I'm going to use our representation with these lines passing through it. Okay, we have A1 here, A1 here, I1 here, I1 here, AN here, AN here, IN here, IN here. Okay, and then we have another cube. Okay, let's use some other letters for it. Say, I don't know, R prime, S prime. Okay, and a triangle. We have to bracket this with P0. So right now I'm going to be very explicit about what we're doing. Okay, and we have to, of course, this resolvent also has we're passing it through, slicing through, right? We're going to hang this circle with a 1 in it to remind ourselves that that's a resolvent in the first power, not some higher powers. And we have to sum it over n, okay, from 1 to n in the resolvent. Because the resolvent is a sum of these various n-body components, okay? Now, let's try to understand this expression. Well, we know, of course, from at the outset, that we need to form all resulting diagrams that have no external lines. Well, that's an easy part. Okay? But please pay attention now closely to what kinds of diagrams we can produce. Remember, that line slicing through has a meaning of phi0 here and phi0 here, okay? And then we have an excitation vertex, okay? E, I1, IN, A1, AN, okay? And here the de-excitation form of it. In other words, the joint of the E. And then we are dividing this by the denominator, which is minus kappa, I1, IN, A1, AN, this times to the first power, so no K, all right? That's the middle part. That's what this, maybe I'll sort of emphasize it. That's what this is. Well, if you really look closely, we have this. Phi0, some stuff, Phi0. And then between the dashed line and this Phi0, I have an expectation value. So this region is an expectation value. The region to the right is also an expectation value because of our interpretation of the resolvent. We have Phi0, some operator part Phi0. Is this clear? That's the essential part to understand. That's the structure of MBPT. That's not the generic structure of a Raleigh expression. In MBPT, you can see that we are factoring this into this region of a diagram, which is an expectation value, and that region, which is an expectation value. But what does this mean? That means that in addition to forming diagrams with no external lines, I have to make sure that all the lines in this region are contracted. That we have no external lines in this region, and that we have no external lines in this region. Well, that means that since we cannot contract these two together because it's a normal ordering, we have to take our S lines and connect them with these. And we have to take the R prime, S prime lines and connect them with those. Okay, we have to, because we have to contract not only overall, fully, but also we have to contract in those two regions. Okay, that's because of the resolvent. Well, so tell me, you're summing over n. Do I have to still sum over all n values? Or maybe I can now limit this. What n do you think I should be using?
We only S available,
So n here would be
just
1. That's the only part of the summation over n-body components of the resolvent that contributes, because you need only 2 lines to contract to these two. Same here, anything here. If you want to fully contract these two with lines here, your n has to be 1. Okay? Well, that's fine, of course, because we have to have the same number of lines on both sides. Okay? Meaning that if I now read this, so if you don't mind, I'll now erase the resolvent diagram. I think we got used to it, I hope. Right? Please make sure that you have it copied. It's going to be in the video, but please make sure that, because that's going to be critical for us for a little while. Okay, so if I start reading this, it seems that the diagram I am really having here, the only resulting diagram will have this structure. There is a Q vertex here, Q vertex here. There is a resolvent between, but only the one body part of it. Okay, only one body part of it survives. The n equal 2, n equal 3 don't contribute because you would have too many lines in the resolvent that you couldn't fully contract. And you cannot contract them with themselves because you cannot contract A with an I. Okay? It's in a normal ordering. So, all right, so what we have is a diagram that looks like this. A, both being free, and then slice through with 1. Okay? Well, that's what it is. Let's read it. Well, if you look at this diagram, obviously you see the weight of it is 1, right? Because, you know, we just have one loop, right, in it. The sign of it is there is one loop and one internal whole line, so it's going to be +1, right? Minus 1 to the 1 plus 1 is +1. The scalar, it's a product of scalars, so. What is the product of scalars? The D factor, AI, okay? Here you have an outgoing line I, Q, incoming line A, times, here you have outgoing line A, Q, incoming line I, but we're not done yet, because there is a scalar coming from the resolvent, that's a denominator, which is, of course, you know, you take, you remember, you read wholes minus particles. So it's epsilon I minus epsilon A to the minus 1. To the minus 1 because we have that 1 here. Okay? That's a scalar. What is then the final formula for K02? With an A, you know, that A component of K02? It is simply a sum over A and I. We have I, Q, A, Q, I, divided by epsilon I minus epsilon A. You see? And that's the first time, you know, if you haven't seen this before, that's your first experience with MVPT. That's how this correction, this part of the correction looks like. Now the question that we can ask ourselves is, do we really need to draw the resolvent to produce such an expression? And the answer is, well, not really. We could simply modify our rules, because you can see that this denominator, the only thing that is left over of the resolvent, see that part, we could read from just the Q's. Yeah? The only thing that resolvent brings us is the denominator. So all, you know, I really could write is the following, draw is the following. I could draw simply the diagram resulting from two Q's, you know, the Qn type Qn expression, all right? And simply adopt the rule. Okay? Label it like we normally would, and adopt the rule, right? That with that for the lines that are between perturbation vertices, with the lines that are between perturbation vertices, we are assigning. So here that one, we are assigning the denominator. How you read the denominator? Whole minus particle. Okay? So we could reasonably agree that we could modify our rules, at least in this case, by adding an additional, let's call it the denominator rule, okay, that tells you that anytime you have lines between the two perturbation vertices, you just slice them through and you read the appropriate denominator, right? Holes minus the energies of the holes minus energies of the particles, okay? And you are done, all right? You know, when you get enough experience, you may actually drop that even. I will keep it because I want to remind ourselves that there was a resolvent here with the first power, not in the second power or third power, okay? But you can see that there's not much left from this resolvent. All the fanciness of it that we sort of introduced, right? It seems like not much is surviving. Okay? Well, so that means that the sort of a rule that is emerging, maybe I'll make a note of it, is this. If I have, say, perturbation vertices, and if I have some bunch lines, I'm not going to collect them in a specific way right now, some lines between them, and it seems like I do have to have them because resolvents are in between. The resolvents have lines. Resolvent is at least one body, so it has lines. Okay? So if I have these lines, say A1, AN, IN, I have to simply slice them. Okay? Slice them with and remember that the power of the resolvent, which was there, and assign a factor, a numerical factor, which is simply epsilon I1 minus epsilon A1 plus epsilon IN minus epsilon AN, and take it to the minus K, if that's the power. It seems like that's the rule that is emerging. That the only thing resolvents that will be bringing are these perturbed denominators in the proper powers, read by simply slicing the lines. Slicing lines. Is this clear to you? Okay, well that was a first example. Let's look at more examples. I guess I will not do a lot more, but let's, I can finish second order, actually. Okay. Let's look at term B. You know, you start in the same way. You have a summation over n. From 1 to n, we have phi 0, okay? You know, K0b is defined as phi 0, Qn, R0, Vn, phi 0, okay? Let's see what we can do about that one. So we have, again, on the left we have a Q vertex, okay? So Rs. Then we have a resolvent. Okay, slice through, power 1. Okay, so again, A1, I1, AN, IN, A1, I1, AN, IN. Okay, and then I have a two-body vertex, which I will draw in a Hugenholz representation. Okay, so R prime, not I don't know. Okay, R prime, S prime, T prime, U prime, doesn't matter, and then phi 0. Okay, that's how the that's what we get for the B component of our expression. So as you can see, well, once again, remember that middle part. Maybe I'll now mark it with a thing, right? That middle part brings in the projection operator phi 0, phi 0. Of course, then there is an excitation here, right? I'm not going to do it, I did it before. And then we have to divide by the denominator, right? That's the middle part, corresponding to this sort of slicing procedure, right? Once again, please note that we have to contract all the lines between this phi 0 and this phi 0, and I have to contract fully all the lines between this phi 0 and that phi 0, okay? So this must be fully contracted, and this must be fully contracted, right? Well, that means that those two lines must be fully contracted with these. We have two lines here, so n on this side should be 1. Right? That's the only choice I can make. But here I have 4 lines. V is in the normal product form. You cannot contract lines of V with itself. So you have to take those 4 lines and connect them with lines of the resolvent. So that means that on this side n equal 2. But here we cannot reconcile this because n is the same on both sides. Resolvent has the same number of lines on each side. So if on the one side you have n equal 1, to produce something non-zero. On the other side, you would have to require that n equals 2. Can reconcile this, so you're saying no contribution. Okay? That term is 0. Could I learn about it without drawing resolvent? Of course you could. Look, just think a little bit for a second. I'm sure you already know the answer, right? Look, if I started by simply drawing just the Q and the V, the two perturbation operators. Q would be this, okay, and V would be this, okay? No resolvent. If I just draw Q and V, of course, if I ask you to form a diagram with no external lines, you wouldn't be able to do it. Okay, you can connect 2 lines, fully contract 2 lines with 4, okay, if you want to do excitation value. So that is certainly a no-go. So we don't need a resolvent to tell us this. You see, resolvent plays no role in this at all. All right? The perturbation vertices tell you the story. Well, if I guess you agree with me that on the same token, that the C component is also 0, because it is V and Q then, in the opposite order. Okay? So you might as well add a conclusion that K0, maybe I'll say here, K0 to C is 0. Similar arguments, right? So it seems like the only, if you permit me 2 minutes, so I finish this, so that I have a fresh start. Okay, if I want to do the final part, the D part, okay? So for the D part, I have 2 V operators right here. So let me quickly do it here, and we'll be done for today. Okay, so if I put Vn here, and Vn here. Okay, that's the D component of our second order. You start the same way, but I think you pretty much expect what's going to happen. I have a V vertex. okay? Say R, S, T, U. I have a resolvent vertex in the middle. Okay? A1, I1, AN, IN, A1, I1, AN, IN. And then we have another V. So R prime, S prime, T prime, U prime. Don't worry if you don't put these symbols, you know. And then we have to produce an expectation value here, phi0, and here. Okay? And we have to sum it over n. Once again, remembering that right in the middle, that line that we are using here to slice the lines, that line has phi0 in the projection operator of phi0. Of course, then you have an excitation operator here, excitation operator here. I'm not going to drop it, I know the essential now, right? And then you have to divide by the denominator. The key is that you have this part of the expression is an expectation value, so you have to fully contract the lines. This one is also an expectation value. You have to fully contract the lines, which means that n equals 2 here, because you have 4 lines, so n has to be 2. And n has to be 2 here as well, for the same reason, meaning that the diagram that results from these considerations is very straightforward. Okay? The diagram that we seem to be producing will be V, resolvent V, and we have 4 lines going through. Okay? Just like that. Okay? A, I, B, J. A, I, B, J. They must be the same on each side. You're slicing it through with the first power. Okay? That's the resulting diagram. So when you read it, you can see that the weight of it is 1 over 4, because we have AB being equivalent and IJ being equivalent. Yes? Then, in terms of the sign, well, you need a Brandau. So that's Hugenholz. For a Brandau, we just need to expand it. That's straightforward, of course, here. 2 V vertices. Okay? And, lines passing through. Okay? So, I think I'm just doing the obvious, but almost done. Sorry a little bit. Stop here. Okay. So what is the sign? You see what we have is 1 loop, another loop, and 2 internal whole lines. So we sign here is -1 to 2 loops plus 2 internal whole lines. That's a plus. And the scalar, you know, IJ, AB antisymmetrized, AB, IJ antisymmetrized, and the denominator. Okay, so let me write the final expression then right away, because I hope, can I do this right away? But I think we know everything that we need to. So what is K02, the D contribution? It is a sum over I, J, A, B. Okay? Then we have, in front of it, we should have actually 1 over 4. So K02 with a D has 1 over 4 as a weight. Sign is plus, so we don't have to worry about it. Then for the numerator, we are just reading matrix elements. I, J, A, B, you know, outgoing, outgoing, incoming, incoming, anti-symmetrized, because that's the Hugenholz case. All right? Times, for this one, we have A, B, I, J. So outgoing, outgoing, incoming, incoming. And divided by the denominator. How do you read it? You know, wholes minus particles. Epsilon I minus epsilon A plus epsilon J minus epsilon B. And that is the famous, I guess the most famous MBPT second order expression. Okay? And again, I hope that it's clear to you now that all the resolvent did to us was the denominator. I could get the same expression from this following picture. Okay? For the Hugenholz, A, I, B, J, slice it through. That would be my Hugenholz. You agree with me that if you just build the diagram from 2 V's, forget the resolvent, and agreed that all the resolvent does is to give you perturbative denominators by slicing the lines, we don't need resolvents. Okay? Is this clear? So right now, as you can see, we already worked out the second order correction of energy. Next time we'll work out the first order correction of the wave function. We generalize this to the rules, and then we'll go to the third order. Okay? And so on. Okay? That's our plan. Is this all clear to you? Okay, great. So please think about your questions for Wednesday. Our class will be split between the lecture part and the question period, part, and then we'll have our midterm exam in the afternoon. Okay, thank you very much. I'll see you Wednesday. Thank you very much.